Possibly, again, hypothetically. Now, it's interesting because in this scenario, the muon-catalyzed fusion, again, has been one thing that was studied at the end of the 1950s and reported on so beautifully. So that's one possibility. It could be something completely different. We don't know until we apply a lot of careful experiments to figure it out. My message to the scientific community is, please, let's figure it out. One possibility is this nuclear effect, maybe muon-catalyzed, maybe catalyzed by something we've never seen before. But the possibility is that there is some evidence for this being potentially a nuclear effect. And this has been seen by microcraters found in these palladium electrodes once they're extracted from the experiment after the excess heat is recorded. And these experiments have been done by Energetic Technologies, where I was in Israel, and by the Navy's Space War Laboratory. And obviously I have permission from both laboratories to show you what I'm about to show you, because I think what I'm about to show you is pretty interesting. Sorry, it didn't come off very well. But again, this is just one possibility. I'm not saying this is what happens. I'm saying this is a starting place where I would start if I went into the laboratory to try to figure this out. One possibility is you could imagine something like a volcanic eruption, sudden release of energy, but at 100 million times smaller scale. And there's some evidence that that may be the case, but then again, it's not been studied systematically. Now, of course, the analogy is rough. I mean, this is geothermal energy. The hypothesis is that this could be a nuclear fusion energy release from D plus D in the palladium. Now, here's the evidence. These are scanning electron microscope images from Energetic Technologies in Israel, the lab I visited. Now, the interesting thing you see is that in the palladium surface, these are about 4 to 5 microns in total extent. There are these apparent regions of extremely hot ejecta, and there have been close studies to see whether the impurity concentration in the ejecta shows some type of thermal process, or whether instead it shows some type of chemical strafing effect on the surface that some unknown component inside the liquid might have created. Again, just don't know, but it is suggestive and kind of an interesting thing to observe. The people in Israel tell me, from their careful analysis, they're almost certain this was extreme heat release, slightly subsurface, and that the ejecta shows the isotopic migrations indicative of a very, very hot liquid ejecta that cooled. Now realize, this electrode was submersed in a lithium hydroxide, deuterated hydroxide solution, so it was bathed in a liquid. And in fact, in their extreme heat release measurements from 2004, they actually show where the electrode, this tiny little electrode, got so hot it boiled off the electrolyte. Okay? I didn't believe that at first. I said, okay, catching them off guard. I want to see corroborating evidence. Show me the thermal control of the thermal control system for the bath that surrounded this. Well, they dug it out. They showed it to me. The computer date stamped agreed with the date. And when I looked at that, this thing ejected or emitted so much heat, it threw the lauter, the refrigerated bath temperature control off, because the heat provided exceeded the cooling power of the refrigerator for the surrounding bath on the experiment. So, I was thinking maybe I can catch them flat-footed. I can't. It seems to me the science was well done. And a number of my colleagues will hate me for saying that. Now, when you look at this further too, these are just a few more that show the possibility of multiple clustered areas of extreme heat release in regions on the palladium surface. Now, the interesting thing is, in March 2009, at the American Chemical Society meeting, the U.S. Navy's Space War Laboratory released this data. And they have a different growth technique. It's called co-deposition. So it's a different form of getting the deuteron into the palladium. But the point is, they see regions that appear to be regions of extremely hot ejecta. The Navy lab has gone further. They've thermally modeled what sort of subsurface heat release or surface heat release would be necessary to create this sort of ejecta. And they have concluded it must be of nuclear origin. But again, that's their conclusion that they mentioned in the American Chemical Society meeting last month. And it's suggestive, but if you remember, and for those of you who saw the 60-minute piece, they caught up with Dr. Fleischmann in England, and they asked him if he had any regrets. And he had 2 regrets. One, that he called it fusion. You can't jump there. You have to figure that out objectively. And 2, he regretted the news conference. And he claims he was kind of backed into doing the news conference. But again, those are his words, but not mine. Now, are there any lessons learned here? I sure think so. There is a huge gap between discovering a new scientific process and developing a useful engineered system. There are many, many, many things that can go wrong. This is way pre-Valley of Death stuff. Okay, pre-Valley of Death is there too, but there's also a lot of questions about figuring out what the phenomenology is. What is the underpinning basic fundamental science? We just don't know right now. I gave you my best hypothesis first going in guess. It's just that, a guess. We need to stop speculating wildly. I mean, maybe imagine a piece, and by the way, I really appreciate the extreme professionalism and outstanding approach of 60 Minutes in doing the story. Scott Pelley, Denise Shera, and Sam Hornblower were always very thorough and very courageous in their approach to the journalism. I really appreciate that. But what I mean to say is, imagine a piece that instead of talked about how you could have laptops that go forever and cars that only need a new energy source from time to time, imagine if instead they said, this is the process of scientific discovery. This is the process of how we figure out what's real from a new phenomenology we don't yet understand. Say we engage the public in understanding genuinely what the scientific method is. If we were to do that, I think we would be in a lot less trouble with our media interface than we often are. So often we say things that appear to be promises, and when the public doesn't see the laptops emerge that never need recharging, when they don't see, say, the automobiles that can go forever, when they don't see that materialize, then they hold it against the process of science. And I think we kind of set ourselves up for that by being over-speculative when we see something new and exciting we don't understand. Instead, engage the public in the process, the scientific method of how you make such a determination. Okay? Also, I think it's good to pursue basic science strictly because you don't understand. Who knows where it will lead? Who knows where an infant will be in society 40 years later? Nobody does. It's the same way. New science, you don't know where it's going to go, but that's no reason to stop having new science, right? So now also, I really don't know if this science will ever lead to energy production, but I do know it never will unless we really go there systematically following the scientific method. Okay, mass media, I'm about to get hooked out of here. So mass media needs to approach new discoveries carefully because of that. Research funding always strives to be objective. People do extremely good jobs of that. And the scientific method is a wonderful thing. Use it always, no exceptions, even if it isn't politically correct, even if you're worried that you might get in trouble by your boss if you take a more systematic scientific approach, even if people go, oh, you're just an egghead, just jump ahead. You know the answer, don't you? No, you don't know the answer. Scientific method is a wonderful thing. Use it all the time. Well, thank you.